streaming. There we go. And I am going to check to make sure that the stream is on. There we go. All right, so the YouTube part is streaming. So this way people cannot say that, I need to be reminded every time. Maybe most of the time, maybe a lot of times, but definitely not every time. Yay. All right, so what we'll do today, exciting stuff, is to look at string functions and how to implement certain things in assembly. So basically today is yet another demonstration, of all the things that we have been talking about. To be more specific, we are kind of working on logic and continuing to talk about functions and various ways of combining function calls. So the way I'm writing the C code right now, this is the C code that I'm going to implement in assembly, is it's basically just a string function, and I'm going to use uint8_t x as a local variable. So x gets a value of 2 over here, and then x gets a value of, let's say, 16 over here. What I put into x is not really important as long as they're different. That's just for illustrating how we go to different branches of a conditional statement. So the really fun part is here. I'm using the string length function to determine, what is the length of the concatenated strings str1 and str2. And actually this won't work because string 1 doesn't have any content, so I'm going to use string copy. Or if you guys really wanted to use to be more complicated, I can do something like this. So we can have a string ncpy, string n copy, and we'll put a literal string here, and we can just say hi. Okay, so that's my literal string, and then we have string 2, which is too long. So there we go. Okay, so this is something that we are going to implement today, because this is one of the things that we haven't really explored in the topic of subroutines, is what do we do to integrate the result of one call to a subroutine to be an argument to another subroutine, and then use the return value of that subroutine as the argument to the third subroutine. So that's what we're doing here. And then, but this program also illustrates what strings are really like in assembly language. What do we mean by a literal string, like how string 2 is initialized, and also this is a literal string that is not even attached to a named variable. It's just kind of floating out there somewhere. Okay, so the question is, how is that implemented in assembly? So we got a few things to go to explain today. We'll go ahead and save this file and go ahead and give it a try. So we'll do gcc-g-warn all, and I think it's called strings.c, and we'll compile to strings as an executable. Okay, -o. There we go. And it complains about string n copy and string n cat not having enough parameters. So we need to fix that, because the whole idea of using string n, is to specify the length. And I also forgot, a close parenthesis here. We'll fix that one over here. All right, so fixing one thing at a time. So when we specify string n copy, we have to specify how many bytes we want to copy, and that typically is limited by what we copy into, the limit of what we're copying into, which is string 1 in this case. So we have a macro definition to indicate the length of string 1, and then this one here, where I'm putting a limit here, that's related to string and cat, okay, which is a concatenation. All right, so we'll save the file again. I think it's already saved. And we'll go ahead and take a look at the man page, or the manual page of these content. So we'll first take a look at string length, which I hope is not new to any one of you, because string length is a fairly basic string function in C and C++. So string length, all it does is to compute the length of a string, so that it's counting the non-null bytes until it finds the null byte. So the null byte is not included in part of the length because it is considered as a terminating byte, which is not considered part of the content of the string. So that's one. The next one we want to look at is string and cat. So string and cat, which is over here, is string concatenation. We are basically concatenating the source string to the end of the destination string, but we'll limit the size to only n bytes. In other words, we'll never copy more than n. We'll make sure that the destination string is no longer than n bytes. That's basically what the n is for. It should be indicated here. If source contains n or more bytes, then string and cat writes n plus 1 bytes to destination, n from source plus the terminating null byte. Therefore, the size of dest must be at least string length of destination plus 1 plus n plus 1. Oh, okay, so this one is actually not what I think it would be doing. It's basically, it doesn't quite catch how many bytes the string already, destination already has, and it will basically copy at up to n plus 1 bytes from source to destination. That is not good. Okay, so that makes it kind of dangerous because it is not forcing a limit of how many bytes the destination can have, at least not clearly. So I'm going to change the program a little bit so that it is not going to do that. Alright, so we'll probably just ignore the string cat for the time being, and we'll just use string and copy. There we go. So I apologize for having to change the code like right away, but that's because I don't want to encourage unsafe type of programming. So we'll simplify it to just a string and copy, where high exclamation point and a null character is copied to string 1, and we'll copy up to string 1 length, and that's including the null byte. And then we'll compute the string length of that and see if it's greater than 6. If so, x gets a value of 2. If not, x gets a value of 16. And that's what the main program is supposed to do. It's not anything that's particularly helpful. Okay, this is definitely not something that's really useful, but it is still useful enough to so that I can show you guys how several things are done. Literal strings, and we don't have string 2 in this case, so we can kind of ignore string 2 for the time being, and then later on we can kind of use string 2 for something else. Alright, so we'll go ahead and write this program. Okay, I intentionally put a control structure here just so that I can also illustrate how to compile control structures in this context. So do we have any questions about the C code that we are going to convert into assembly code in today's class, in today's lecture? Alright, so there are no questions so far. Okay, cool. I'm checking out something else here. Okay, cool. Alright, so first of all, we'll go ahead and compile the program and make sure that it does what it is supposed to do in C. And that's one thing that you guys can do too. Okay, so I'm pretty sure the way I want to have our final exam is to have a C code on one side. I'll give you the C code that is compilable, and I'll give you a faulty implementation of that C code in assembly language. So your job, for the final quote-unquote exam is to figure out what's wrong with the assembly code and fix the assembly code. But do not rewrite the entire code. I want people to spot the problems, explain what the problem is, and then give me a solution to fix the problem. So a complete rewrite of the code does not count at all. It has to be fixing the problems. And I'll give you an example tomorrow of the format of the exam. And I'll give you guys 24 hours to do it. So it will be midnight to midnight 24 hours to get it done. So there will be more information on that definitely by tomorrow, and today we'll focus on just kind of learning more concept and more techniques before we get to the practice session tomorrow. All right, Catherine is typing something, and I am going to wait a little bit, but I'm going to get into the executable strings. Okay. Can I show you an example of how to run this C program to confirm how it should behave? Yeah, that's definitely the case. That's exactly what I was trying to do. Except it didn't do it. Alright, so did I get an error? Yep, I got an error. That's why. So unknown type, okay, I forgot to pound include standard integer.h, and that's why it did not. Compile. There we go. Alright, so this time it should compile without any error. Okay, yep, so there's no error this time, and I can see that the executable is refreshed. So now we can gdb strings, list the program, and we'll do it step by step. We'll put a breakpoint on line 14, and we now run the program. So what this is doing is it will first call string end copy to copy the literal string high exclamation point to string 1, and then that string 1 is returned by string end copy, so that becomes the argument to string length. So string length is going to take the non-null, it will count the non-null bytes in string 1 until it encounters the null terminator, and then report back the actual length. Then that particular length is now used to compare against the constant of 6 to see if it's greater than. So I'm going to single step, and it's going to complain a lot because I do not have the source code of string length, so that's why it's complaining that we are supposed to be in this assembly language file. Anything that ends with a uppercase s is actually an assembly source file, but it's lacking in my system. I did not install that particular package, so that's why it's complaining. So let me just rerun the program from the beginning, and this time instead of using s for single step, I'm going to use the other option to quote-unquote single step, but it doesn't single step into subroutines. I'm trying to remember how to do it. Okay, so help running. Okay, next, that's it. Okay, so it's next. So when I type next, it continues execution to line 20, which is the else case. And at this point, I can actually see what is in string 1. And string 1 has high exclamation point, which means its string length is only 3. And because the condition is trying to compare the string length of string 1 against 6, to see whether the string length of string 1 is greater than 6, which is not the case, and that's why we ended up in the else case. And at this point, if I next again, it will get out of the conditional statement and stop the program. I mean, we get to the end of the execution of this program. So that's about all this program does. It doesn't do anything particularly useful. All it does is to combine the calls of several subroutines. All right, so let's get back out to the source code itself, which is right here. All right, so the key is we are using the return value of string end copy, which is this portion, to become the argument to string length. And then we use the result, or the return value of string length, to compare to the constant of 6. And then based on that comparison, we decide what we want to do with the conditional statement. Should I get to the else branch, or should I go to the then branch? So that is determined at that time. Okay, so Catherine is typing something. So one thing about this program, what is the significance of the constant? And I'm assuming Catherine is referring to string 1 length, str1 len. Okay, so that's called a macro definition, and a macro definition is processed by the CPP or the C preprocessor. So anywhere the C preprocessor sees the name of str1 len or uppercase, it's going to replace it with whatever text is defined to be the macro, which is 4. It's used here because instead of having me to remember how many bytes is in string 1, I'm using a constant, so that when I want to perform a string and copy and want to make sure that it is safe, I can just use whatever string whatever the actual length of string 1 is, instead of having to spell out the 4. If I were to use 4 over here, then I would have to remember to use 4 over here. Yes, it only copies up to 4 bytes. That's what string and copy does. Yep. So to further understand what is string and copy, we can look it up. So this is the definition of string and copy is right here. So it is similar to string copy, except that at the most n bytes of source are copied. If there is no null byte amongst the first n bytes of source, the string placed in destination would not be null terminated. So that's actually it's in its own way kind of dangerous. If the length of source is less than n, string and copy writes additional null bytes to destination to ensure that a total of n bytes are written. So are we okay so far? So that means that if we're copying from a string that is shorter than n, then it will copy the entire string from source, but make sure that destination is also going to be null terminated. Yes, so it will not overwrite more bytes than n, but it does not always guarantee that the null terminator is there. It will only copy as many bytes as source is providing. So if source is an empty string, then it will copy 0 bytes from source and then immediately put a null terminator at the very beginning of destination. In fact, we are going to implement string and copy ourselves, so we'll go ahead. It does not fill it with null terminators. It will at the most fill it with one single null terminator. I take it back. If the length is less than that, it will fill it in with null bytes to destination to ensure that a total of n bytes are written. So Catherine is correct that it will fill it up with null terminators if the source is not doesn't have a string length of n, has a string length that is less than n, I should say. All right. So we're going to implement string and copy first, because I want to also show you how to translate that into assembly code. Okay, so we'll go ahead and go back to the editor window, which is right here. So the first thing we want to do is to implement our own string and copy. So we have char star string and copy, and it has got 3 parameters. The first one is the destination. The second one is the source, which is specifying where we are copying from. And the third parameter in this case is the length. But since we have a small processor, so I'm going to use uint8_t to specify n, which means we can only specify up to 255 as n. Now the actual real string and copy can handle a long, which is a 64-bit integer, but that's okay because we are just really trying to do this. So we'll make sure that this is my own string and copy, and we'll change this to use my own string and copy here as well. There we go. All right, so now we need to implement string and copy. There are 2 ways to do it. I can do it using recursion, which is awfully inefficient, but it is actually not bad to look at, okay? And it's a different way of thinking about things when you do things using recursion. I can also do this in a more conventional way of using a loop, which is what we'll do today, at least at first. Okay, if I get enough time today in the lecture, I will re-implement this function recursively, just so that you can see how something that is implemented in a loop using while can also be implemented using recursion, which involves a conditional statement and a recursion. But we'll save the fancy stuff until much later. All right, so the first thing we'll do is we'll have a local variable, and we'll call the local variable just PTR, and we're going to get it initialized to destination because I need something to tell me, where I can copy to. So now the question is, what do we do, to do all this copying? So the thing is, I'm using n as a counter. Okay, so we'll say when n is non-zero, we'll do the following. The first thing we do is we are going to copy from, we'll check a few things. Okay, so I can do this in two loops. The first one is to copy whatever source has into the destination, and then the second loop will fill it with null terminators. We'll fill the rest of the destination with null terminators. All right, so now the first thing we need to do is to see, do we have anything to copy? So we can specify that as part of the condition too. So now we are saying as long as we have enough bytes left over in the destination, and whatever the source is pointing to is a non-null character, we have not reached the end of the source where we're copying from, then we'll perform whatever is specified in this loop here, which is simply only copying one single character from the source to the destination, but it also has to advance the pointers to the next byte, and also decrement n so that we remember that there's one fewer byte to copy. So the first part is easy. Okay, we just copy. We don't use destination. We use PTR, the pointer, which is my local variable, and we say let's copy one byte from source to where the pointer is pointing to, which is a part of the destination. And then second thing we want to do is to increment both of the pointers. So PTR is incremented to the next location, source is incremented to the next location. But we also have to remember to decrement n. Okay, n minus minus is fine too, just to be consistent, because we have now used up 1 byte in the destination to store 1 byte from the source. So when this loop terminates, it has to terminate because one of these two conditions is false. If n is 0 already, we really don't want to do any more copying, and we are pretty much done. On the other hand, if n is non-zero, that means we got out because we found the end of the source. Okay, because this loop is not going to copy the null terminator from source. As soon as we find the null terminator of source, we get out of the first loop. So the second loop can be done in this particular fashion now, as long as n is non-zero, as long as we have room left over in the destination, we'll do the following. Okay, we'll just say that I'm going to use this notation here, and we'll find out what it can do, what we are actually doing later on. Okay, this is a post increment operation, which basically means the increment to PTR, okay, on this line, the increment to PTR does not happen until this statement is entirely done. So it is actually equivalent to not having the post increment operator and then have the post increment on the separate statement after this statement here. So these two notations are the same, except in C and C++, it allows you to do a plus plus in here so that you don't need a separate statement after that. It's basically just a shorthand. This is the longhand of doing exactly the same thing. So when the second loop completes, that means I have used up every single byte in the destination, which is what the man page is telling us that we need to do. And what is returning is just returning the destination itself. That is also part of the specification of string and copy. So now with this in place, we're going to rerun the program to make sure that my implementation of string and copy is also correct. Okay, so we'll save this file, go to the command line. Nope, not this one. We'll go to this one and just recompile the program. And we got some warnings only. Okay, those are only warnings. I'm just looking at this and see if I should okay, I see. Okay, so I need to fix one thing. We are seeing so many warning messages because I declared the type of one of the local variables incorrectly. String 1 really should not be a const char string because we do intend to overwrite the content of string 1, so it really should not be a const char array. It should just be a char array. So that should fix quite a few of the warnings that we have seen here. So let me recompile. So it got rid of a few. Implicit declaration of the string length function. So string length, interestingly, is not a part of string lib or standard lib. It's a part of string.h. So we're going to have to include that. It's doing this automatically. So the compiler is saying, oh, I see that you're using string length, so I'm going to automatically pound include string.h. So let me just explicitly put it in. So this way we get rid of another warning, like so, and then go back and recompile, and hopefully we get rid of most of the warnings. So this time it's only complaining about x, and it's complaining about x string 2 because we did not use string 2 in the program as it is right now. So everything is good, and now we can go into GDB, and this time we can do exactly the same thing as last time. We'll put a breakpoint on line 36, which is the then branch of the conditional statement, and we'll also put a breakpoint on line 40, which is the else branch. So I'm not stepping into text string and copy, so this call is not being tracked either, because I just want to see to make sure that it is working correctly. So now we run the program from the beginning, and we are getting to the else branch. So it's time to print str1, and it does have high and exclamation point, and there's a null terminator right after this. Okay, that's just implicitly there. All right, so the program works exactly the same, which is not a proof that my implementation of string and copy is correct all the time, but it does, verify that it does work in this particular case. So our job is not really to look into the correctness of string and copy, but to implement string and copy and also everything else in main in assembly. So now we look into the assembly code side. Okay, so we start with a no op because I think it's probably a good idea to run this in the CLI mode of Logisim. And then we have a JM. Well, okay, so just so that it is clear that we initialize the stack pointer to basically 0 0, and then we have a JMPI to main. So this way, oops, without a colon. So now we are going to implement text string and copy. Text string and copy. So just like usual, I want to know what is on the stack. So this time we got quite a few items on the stack. We got n, we got source, we got destination, then we got the return address back to the caller, and in this case we also have a local variable which is PTR. Okay, and at the very entry point, at the beginning of the entry point of the subroutine, the stack pointer is pointing to return address, which is not where I need it to be, because I really need the stack pointer to point to the lowest item of the frame. The frame in this case would be these 5 items. So these 5 items together, forms the frame of an invocation of text string and copy. So I need the stack pointer to point to the bottom of the entire frame, which means I need to do a few things. Okay, so we need to define PTR to be 0, because the offset from where the stack pointer to point to PTR should be 0, even though it is not the case at this point. So we're going to fix that with some calculations on the stack pointer. The next item is the return address, which is not something that I need a label for. Just like before, we have a label, to define how many bytes are used by local variables. So in this case, I can use the full name, which is text string and copy local var size, It is really long, but it still works. Okay, it's PTR1 plus. PTR is referring to the local variable that is using the highest address, and then this one is referring to the size of that local variable. But since pointer is just a pointer, which it's only 1 byte in the toy processor. So after that, we can define destination. So destination is text, string, and copy local var size 1 plus. This one here is referring to the byte that is used by the return address. So we add up all the local variables, and then we add 1 to it because we need to account for the return address, which is also sitting on the stack. I don't really want to define this label to be return address because there's really no need for any C code nor assembly code to access the return address. Now there are a few really kind of tricky things they can do with this, but it's not going to work in general in C, so I'm not going to introduce those tricky things that we can do with messing around with the return address. Then we got source, which is destination 1 plus, and then we got n, which is source 1 plus. So these labels now define the various things that we need to know about the frame of text, string, and copy. So now it's time to actually allocate the space that the local variables are using. So in this case, we only got one single local variable, but we still have to allocate for it. So the way I usually do it now is to load that constant into register A, B, or C, and then we do a subtraction to basically decrease this much from the stack pointer. Okay. And by the way, I have been looking at not finished grading yet, but I have been looking at the submissions of the previous homework assignment, and I found that I think, okay, this is just what I think because I don't have any solid proof, but I think some people just really kind of copied and pasted the code and just add something to it without even running it through the assembler, let alone running the code. So that doesn't help those people to understand the concept. I think those people did it in a rush, just kind of copy, paste a little bit, add some code to it, but they did not even bother, as far as I'm concerned, to run it through the assembler. And if the assembler is not going to work because there are syntax errors, then it's not going to run, and that is not how we write or debug programs. So that's not going to be very helpful. So I'm hoping those people will kind of try more to use the assembler and use the simulator to run programs so that they can actually see how the programs run and understand the concepts accordingly. Okay, so now we have the usual exit code, and you can probably see that this is really a template at this point. Okay, as long as you define the labels correctly, this template is going to work. Whether you have local variables or not, whether you have one or more local variables, it doesn't even matter. Okay, as long as you have this label defined correctly, this template of code would work. So now at this point, we got the frame all set up. Okay, if you want to look at what the frame looks like, so I'm going to use the other approach now. Whatever is on the left hand side has a high address, whatever is on the right hand side has a lower address, and whatever the stack point is pointing to has brackets around it. Okay, so this is what the stack looks like. We got n, we got source, we got destination, we got our return address, and we got our PTR, which is our local variable, and that's where the stack pointer is pointing to at this point on the stack. Okay, so this is a much more compact way of looking at what is the content on the stack. And at this point, now we can start to implement the program. The first thing we need to do is to initialize. Let me turn on line numbers here and also here. So the first thing we need to do is on line 11, the allocation of the space is done at this point, but we haven't really done the initialization yet. So now we need to implement the initialization of the pointer on line 11 of the C code. So at this point, I don't think this is anything new to us, hopefully not, but we should understand how it works. Okay, in the final exam, okay, on Thursday, I might give you a sequence of instructions that can accomplish the same thing but differently. Okay, so have to understand the effect of the code and not just kind of not just memorizing what code works in my examples, but you also have to be able to look at a new sequence of code and figure out what it does and see if it's doing exactly the same thing as some existing sequences of code that we have encountered time and time again. Okay, so that is going to be the challenge, is you will see new sequences of code that will do the same thing done, but you have to figure it out on your own. Yes, absolutely. So Catherine was asking, would we do that by running it? So you can run it and understand how it works. Especially if you use the trace analyzer, that would be very helpful because you can go back and forth. You can go forward and backwards using the trace. You can also statically just analyze the code by looking at the source code. So that works too. But that's going to be the key to not to answer, but the key to fix the code that I'm writing is to really track down what the registers are doing, what they intended to do. I would actually write comments and say that this chunk of code is corresponding to which part of the C code, to give you a clue of where you're supposed to be at in the C code. So you kind of have to think about what the assembly code is doing and do the minimal change to fix it, and not to rewrite it from scratch. All right, so now we're gonna have the add instruction, because we need A to be the address of the destination, and that is on the right hand side. So we are going to do LDAA because we need the value of destination, and now we need to store it to PTR, which is on the left hand side. So now we need to do something about the same, LDIB to from PTR. So I will answer Catherine's question after I get this part done. Okay, so that should accomplish line 11 in the C code. Catherine is asking, can I give you easy examples before the exam to work through? I got you some of the examples already, because in my notes in the past, I use a register C. I basically use a CPR CD to copy the stack pointer to register C, and then I use increment and decrement of C to move C around to access different items on the stack. So that part is already kind of done in that particular fashion. In the notes, I'm not 100% sure, but I think in one of the labs that was used, that was the approach in one of the labs. Pretty sure about that. Yeah, so I think that in the labs I already introduced that particular method of accessing various items in the frame. I can even illustrate it here. So whatever I illustrate here is obviously not going to be the only way I'm going to use in the final exam. So I'm gonna keep I will come up with slightly different ways to do things in the final exam. And then the other thing is you also have to kind of keep track of what is on the stack, because sometimes I would say, hey, this thing is kind of difficult to calculate, and I know I need it back later on. I might push it on the stack so that I can retrieve it later. So that means when you analyze the code in the final, you also have to kind of keep track of what is on the stack at any time during the execution of that code, and so that's why commenting is going to be very important. All right, so getting back to this code here, line 11 is now done, and now we are moving on to line 12. So line 12 is the beginning of a loop, and the way I label or structure a loop is like this. Now, whether you guys want to do it this way or not, it is entirely up to you. So at this point, I'm going to abbreviate text string copy as just kind of stcpy. Okay, strings text string copy, actually tscpy. Okay, text string copy. Okay, and I'm going to define a few labels first. Okay, so I will define this label as while one begin, because there are two while loops. So this is the beginning of the first one, begin. There we go. And I will immediately define the end. Okay, so it's text string copy while one end. Okay, and right before the end, I'm going to do a JMPI right away to TSCPY underscore while one begin. And I do this because this is the structure of a while loop. Okay. Now, how do we get out of the loop? We have to specify some code here to specify when or how we get out of the loop, but I'll do that later on. I do the structure first. Okay, where's the beginning? Where do I get back to when one iteration is done? And I will put in the JMPI right away. Okay, so I don't forget. And I'll also define the label that marks the continuation after the loop right away, because these things are pretty easy to type at the same time. It's like only 3 lines of code, but this way I do not forget to do it later. Okay, because one of the things that this is something that's specific to me, is I will forget to do this later. Okay, if I don't do it right away, I'll forget it later. So that's why I do it right away. When I open parenthesis, I close it right away, and then I go back in to fill in whatever is in between. Now, whether you find this useful or not, that's up to you. Okay, that's entirely up to you. So now we need to look at n and see whether n is non-zero or not. Okay, so once again, we can. Okay, here is one thing that I can do. Okay, I'll give you guys a clue of what you can expect. Is I can do a CPR A is fine. So CPR AD, and instead of using the offsets and stuff like that, I can still use the offset, I suppose. But it's not nice, to do it that way anymore, because now I have to manually calculate where n is compared to where the stack pointer is. So I can do a whole bunch of increment A, to get to the address that I want to get to. So that's one way to do it, but I can also do it in a very clumsy way, like LDI B with n, and then we can add BA. So I know this is really the same thing as just using the stack pointer, except I wouldn't need the CPR to begin with. I type KKK not because of the reason that people associate KKK with. It's because in VI, if I want to go back up 3 lines, that's the letter K. Okay, so I just want to explain that before people go like, wait, hold on a second here, tag is da da da. No, that's not the case. I just wanted to get back on 3 lines, because I want to get back onto this line to mention that this line is really not needed, because I never really modified register A, so I could have just used register D here instead of using a CPR first. Okay, but it would do the same thing. Alright, so at this point B is the address of n, and I'm going to do LDAA, and I want to see whether it's 0 or not. So this is not a real comparison, it's just checking whether it's 0 or not, and I can do that by using AND AA, and then the JZI is the only conditional branch that I can utilize. But in this case, it is actually appropriate, because if n is 0, I want to get out of this loop. So I'm going to go to the exit label corresponding to this loop right away if n is 0. The second thing I need to do is to check source, which is a parameter, but I'm not checking whether source itself is null or not. I'm checking whether what it points to is null or not. JCI is the only one I can use because I want to know whether A is 0 or not. We don't have a conditional branch to say that, what if it is not 0? So that's why I said, JZI is the only thing I can do here. Right, so I need to check source at this point. So this time I'm going to do the usual, easier approach. So we're gonna, I'll use a different register. Well, I can use the same register, I suppose. Add AD, LDAA, and LDAA, because we are dereferencing source, and check whether that is null or not. Now, if you can kind of look forward a little bit and see that on line 14, we need to refer to source, you can kind of track that too. So at this point, we'll do an AA again, JZI to get out of the loop. because if whatever source is pointing to is null, that's my other reason to get out of the loop. To stay in the loop, I need n and whatever source is pointing to, both to be non-zero. So if any one of them is a 0, I get out. All right, so now we get to the actual body of the loop, which is on line 14. So at this point, we are going to copy whatever source has, which is still in register A, to whatever PTR is pointing to. So I'm going to do LDIB, choose a different register for the left-hand side, add BD. That would give me the address of the parameter. So in this case, I need to do one dereference first. Now, at this point, okay, if I look ahead a little bit, I know that I need to increment PTR, which is my local variable, on the very next line. So that means if I put it into yet another register, let's say C, then it's going to be advantageous because I don't have to reload things all day long at this point. Okay, so now I have A, B, and C all being used at this point. You kind of have to remember what those registers are. So I will give you a line of comment here. A really is referring to whatever source is pointing to, not source, but whatever is pointing to. B is the address of PTR, and then register C is PTR itself. Okay. All right. So now I need to perform the assignment operation. So the assignment operation is copying whatever source is pointing to whatever PTR is pointing to. So I know, okay, it's going to look like this. The question is, what should I put in the parentheses? Now we know register A is ruled out. Okay, register A is whatever source is pointing to. It's not going to be it's not the left-hand side. But both register B and register C relates to what we need to do. So now the question is, which one should I use? Should I use register B or should I use register C? I'll give you guys a moment to think about it. You can rely on line 47 instead of tracking down the code to figure out which register has what. So based on the assumption that line 47 is in fact correct, which one should I use? Register C is correct. Okay, we are dereferencing pointer, so we want to use as STCA. So after this instruction, register C is not useful anymore. Okay, so I can reuse register C for other stuff. So now we're moving on to line 15. Okay, so when we get to line 15, we want to add one to the local variable PTR. We are not adding one to what it points to, we're adding one to the local variable itself. This is where register B comes in handy because register B has the address of PTR, but register C is still useful because I'm adding one to the value of PTR. Register C has the value of PTR, so incrementing register C is the correct thing to do because I'm incrementing the value of PTR. But when I need to store, I need to store it to whatever B is pointing to because register B has the address of the local variable. So this is where things can get a little bit interesting because when I try to reuse registers across statements, then you also have to kind of track which register is containing what useful information at that point of execution. Now, if you trace this through using the CLI, using the trace analyzer, that is very helpful as well because as long as you know which part of memory belongs to what concept in C, it will be very helpful. So I claim that this is done. We are done up to line 15. So now we move on to line 16. We don't have a single register to store the address of source because, well, guess what? We only got 3 registers to play with. So unfortunately, this time I actually do have to recompute the address of source. It's not too much, it's just kind of a chore. Okay, so we put it into here, add AD, and then we do a LD to get the value. But I don't want to destroy A this time. Okay, I can destroy B because B is PTR is not useful anymore. So now register B has the value of source, register A has the address of source. So when I increment, I'm incrementing the value, then I store it back to where I got it. Okay, so lines 53 to line 57 is implementing line 16 of the C code, which is just incrementing the source pointer. And now I can decrement n, kind of the same deal. Okay, LDIA with n, add AD, and then we do a LD BA, and this time we have a decrement B, and then a STAB. Okay, so that accomplishes line 17 of the C code. And at this point, I'm done with the conditional, the loop. So I just go back to the beginning, reevaluate the condition, and see if I can get out already at this point. So do we have any questions about the first loop in text, string, and copy? All right, so apparently no questions at this point. All right, so the second loop. Okay, so let me move on to the second loop in C. So now we are moving on to the second loop, which is kind of more of the same thing, except it's a little bit simpler. The condition of the loop itself is a little bit simpler, and what we do inside the loop is also a little bit simpler. Okay, so it's not going to be as involved. Okay, but nonetheless, this is yet another loop. So tscpy, which is the prefix of the function. So this way, I do not have to worry about the rest of the label, having duplicates, between functions. So now we have the second while loop, and that's why it's while 2. And this is the beginning label of that loop, and that's why I use the word begin. So this is just how I do it. Okay, while 2 end, and because it works for me, but you have to kind of decide what works for you. Okay, I name my labels in a very kind of systematic way, just so that it makes sense to me. But does it make sense to you? That kind of really depends on how you code. So now we can go back to this line here. We want to see if n is 0 or not. Okay, and Sakil is asking, JMPI is the while loop essentially. No, JMPI is the same as a goto. All it does is to say, let's continue execution based on whatever address you specify as the operand. That's all JMPI is saying. Now, the location of this JMPI is important in the while loop because it is going back to the beginning of the loop so that we can re-evaluate the condition. So am I answering the question? Okay. Yeah, so JMPI itself does not indicate the use of a while loop. JMPI is simply saying I am unconditionally continuing execution at a particular point of the program. That's all it's saying. All right. So I'm just checking on the time right now, making sure that I'm making reasonable progress. So we have LDIA and add AD and LDAA and AA. JZI, if it is 0, we get out. So this is where we have to be careful, okay? Because I have to make sure that I'm exiting using the correct label, because I got two exit labels for the two loops. If I use the wrong one, it is not going to be a syntax issue, so the assembler won't be able to catch it, but the program would go kind of crazy, right? So just kind of imagine what happens if I change this to a while 1 instead of a while 2. It's just going to go back to here. And so the loop is going to become an infinite loop because it will never get out of the loop because I used the wrong label. So that's why it is important to kind of pay attention to the label names and kind of make sure that you don't jump to the wrong label when you have multiple labels that have about the same name but not exactly the same. Alright, so now we just need to copy a 0 into whatever PTR is pointing to. So once again, we have this, okay, APTR, add AD. So A is now the address. I want to keep it around. So I have a LDB A. So the register B is the pointer value, and register A is the address of the pointer itself. And then I use register C as a 0. Okay, so that's loading C with a 0. But there's another way to reset register C to 0. Okay, I'll show you the other way. Oops. Oh no, don't. There we go. Okay, so the other way to reset register C to 0 is to do a sub CC. Because when you subtract C from C and put the result back into C, guess what you're doing? You're resetting register C to 0. So this is really the same as LDI C0, sort of. The only difference between these two is the sub instruction would actually affect the flags. So in this case, the Z flag will be set, every other flag will be cleared, but the LDI instruction does not change the flags at all. So there are minor differences between these two instructions, even though they seem to accomplish exactly the same thing. So once again, where do I store C into? Okay, we got register A or register B. So which one should I reset to 0 at this point? So just want to see if you guys have been tracking the use of the registers at this point. Register B is correct. Very good. Okay, good job. All right, but I still don't want to destroy register B. I'm now done with line 21. So I'm moving on to line 22. I need to add one to whatever PTR has. PTR is my local variable. The address of PTR is still in register A, which is good. I don't want to mess around with that. I'm incrementing B because register B is the value of the pointer. So I want to add one to it, and then I want to store it back to whatever A is pointing to, because register A still has the address of the pointer at this point. So I'm now done with line 22, moving on to line 23, which is really more of the same thing. Now, if you're thinking this is really boring, aren't we doing really the same thing over and over and over again? If you're feeling that way, congratulations. I mean, literally, really, congratulations, because that is exactly what we are doing, is the same thing over and over again. So let me just double check, okay, from line 84 to line 88, okay. Line 84 loads the offset, line 85 computes the address of n, line 86 gets the value of n, line 87 is computing n plus 1, and then line 88 is storing n plus 1 back to n, because register A still has the address of n. So that seems to get the job done. Should it be register B? Should what be register decrement B? Oh, decrement instead of increment. You're correct. Yep, we should be decrementing. Thank you. Good job, June. Catching that. So all of these little mistakes that I have been making, they might appear in the final. So you guys can kind of get an idea of what kind of things can go wrong when I implement the code in the exam. All right, so we are pretty much done, except we have to return the destination as my return value. So this part is LDIA dest add AD LDAA, because this time I don't really need to keep the address of destination around anymore. So that should conclude it. Okay. But I can't, well, I suppose I can test text string and copy by itself. Okay. So let's move on to main. And I'll do the same thing in the C code part. Okay. The first thing is I want to define the macro string 1 length. Okay. And that is just string 1 length colon. And then whatever we want to define it to be, which is a 4 in this case. The assembler doesn't have a true C preprocessor, But labels do kind of the same thing as a preprocessor macro, so we can kind of use those two somewhat interchangeably. Okay, so now here's the tricky part. Okay, we got a few local variables, and how do we allocate for those local variables? That becomes the next question. We'll start with str1. So we have str1, we have str2, and then we have x. Okay, all of these are local variables of main. So the way the compiler does it, which is not the same as something that I did in one of the labs, but the ordering within local variables is not defined by the compiler standard. Okay, so they can be ordered in any way. Most modern compilers would look at str1 as the one with the lowest address. No, I take it back. It's going to be the one with the highest address. So x, which is the last one, is pushed last, and that's why it has the lowest address. So str2 is the second lowest, and that is just x1 plus. Now, you look at this, the definition of string 2, and say, but string 2 is supposed to be, the literal string of too long, and that's going to take up a lot more bytes. That is actually not the case, because str2 is still really just a pointer, and every pointer has the same size as all other pointers. So in the toy processor, a pointer is a pointer, and it only takes up 1 byte. So now the question is, where are we going to store that literal constant of too long? That is a question that we'll answer in just a little bit. Okay. So now we're moving on to string 1. Okay, string 1 is str2 1 plus, because str2, if you look at the size of it, it's just 1 byte. So str2 is just str1 is str2 1 plus. Now we need to define the size of all the local variables. So now we have main local var size. This is now a little bit tricky, because string 1, okay, the way it's defined in C is it's an array of characters. So that's why the actual size of string 1 is str1len. Okay, it will take up that many bytes. So when you look at main local var size, it's going to be str1, which is the label of the local variable that has the highest address, and str1len, which is the number of bytes in that array, plus. So that will be the actual size of all the local variables added together. Is that okay? Does everybody kind of understand how lines 105 to line 109 are doing? Can I do what again? What about the size of str2? That's just 1 byte. Show us. Okay, it's still not telling me what that is referring to. The calculation. Alright, so x has 1 byte. str2 is also just 1 byte because it's just a pointer. But str1 has whatever str1 length is specifying in terms of number of bytes, because it is an array. The string that str2 points to are 4 bytes, but it's not on the stack, and that's why it is not part of this calculation. Okay, so that's the important part. str2 is really, as a local variable, it only takes up whatever length a pointer is going to take up as far as a local variable is concerned. The literal string too long in double quotes is not really stored on the stack. It is actually stored somewhere else. That is the important part. Alright, so now we get into main and we do some initialization. The only initialization we have to do that is implicit is str2 has to be initialized. Now I know the str2 is not really used in this program, but it is important to illustrate how it is initialized. There are a few ways to do it. Okay, it all depends on how you want to do things. First of all, we have to define too long as a string of bytes. So that's going to be a little bit tedious because I did not build the assembler to deal with strings. So you have to kind of figure out, the individual ASCII code of things. So I'm open up an ASCII code table on the side, which you cannot see. You can kind of see it barely at the corner over here, okay, but I'm moving it off screen. So we have too long, okay, which is so now we're using the byte directive, which we haven't really used before. Well, actually we did use it before, but but not very extensively. So what byte does is it's just allocating 1 byte in RAM, not on the stack, okay? So the byte thing is actually in the same space as all the instructions, okay? So that can cause an issue. I'll talk about how to get around that issue. So, but at this point, we just want to define too long. So we look up lowercase t. Lowercase t has an ASCII code of 116 in base 10. And then O is, let's see, 111. And so we got 2 of those. And then we have a space, which is the 32. And so on. Okay, so instead of typing out the entire too long, I'm just going to say it's 2 with a space. Okay, a null terminator has to be defined explicitly. Okay, so even though a null terminator does not appear inside a literal string in C, when you actually initialize it and look at the memory corresponding to that string, it is explicit. It's stored amongst the instructions because it's you can kind of see it as a constant, but all literal strings are living inside the same space as basically the code. It is in a space where it's not supposed to be changed. Okay, so now the question is, when we execute this program, we're going to have a problem because main is going to take a look at the binary, the byte, representing 116, and it'll try to run it as an opcode, okay, unless we do something about it. So this is why we have to do something about it. So we can always jump around it. So we can always say, JMPI to main continuation point 1, and then we defined main continuation point 1 over here as a label definition. So as far as main is concerned, these bytes are really it's there, but it's not going to execute those bytes as locations. But we also need to use a label so that we can refer back to this location. And I'm going to use underscore to begin this thing here. So we'll say this is string 1 const str1, because it is a constant string that I need to refer back later on. So to initialize str2 at this point, okay, we need to first allocate the space for all the local variables. So that's all done before the JMPI. So we LDIA with main local var size sub DA, okay, and then we copy and paste this to the end, and then change the subtraction to an add, and then a halt instruction. So this way we don't forget to deallocate the local variables. So at this point, okay, we can now do the initialization. We can do the initialization before or after this, because as far as execution is concerned, line 114 to line 121 doesn't do a single thing. We can do it anytime we want to. Now, if you don't want to have to jump around, you can actually move line 115 to line 120 to after the halt instruction. That works really well as well. Okay, so let's do that. Okay, so we're going to move line 115 to 120, and we want to move it to 126. So if I move that out of the flow of the main program, then it doesn't interfere at all. So all of these are equivalent. They're all okay. I personally just don't want to waste extra cycles doing the JMPI instructions. But the good thing about doing the JMPI approach, which was before I made this change, is the definition of the string stays local to where I used it. Okay, that's pretty much the only thing that's good about it. All right, So now we need to initialize str2. So this is how we do it. So we do LDIA with str2, which is a thing sitting on the stack. Anything that is just an offset from the stack pointer, you better remember to add the stack pointer to that offset. So now we have the address of str2. We're going to load B. Now this time it is just const str1 with an underscore, and without the add bd. That's because const str1 is not an offset from the stack pointer. It is an absolute address in memory. So now we just need to do a store AB, and this is how we initialize string 2 as a const char pointer. Is that okay? Okay, David is asking a question. I'm gonna wait a little bit. The content of str2 is too long, not str1. That is correct, but str2 is actually not used anywhere within this program at this point. So that's why it's not kind of relevant, but I want to show you what we need to do when we have a literal string in this case. Okay. Yeah, it's just a constant string one. It doesn't really have it has no name. Literal strings typically really does not have a name. str1 is referring to this, str2 is referring to this. This is a constant string, so this str1 has nothing to do with the local variable str1. I mean, you can change the name to something else. You just have to change both of these, at the same time consistently. So, anything you want to change it to is fine. Okay. You can, okay. I suppose you can, change it to const, too long, okay, if you want to. And then over here, you change it to what is actually quote-unquote defining. Even I was too lazy to actually finish spelling out too long in ASCII code, but you can kind of imagine that it would just take up some extra bytes. Okay. All right, so now we get into the actual code, which is kind of really the only part that I want to illustrate today, is how do we utilize the result of one call to call another subroutine. So we have to call a text string and copy first with these items. Okay, so the first one is pretty easy. String 1 length is just really the constant I need to push on the stack. So LDIA with str1 len, decrement the stack pointer, stda. So that way we got the last parameter pushed. Then we have to define high. Okay, so we'll define it over here. So we have const high, and once again, we just have to look up the ASCII table. Lowercase h is 104, and lowercase I, which is right after, is 105, and exclamation point is 33. And don't forget the null terminator. The null terminator needs to be there explicitly. Okay, so now that I have const high, I can now push the address of that literal string which has no named local variables associated with it. So LDIA with const high, decrement the stack pointer, stda. So now we have pushed the so-called literal string on the stack. Okay, it is not the characters that we're actually pushing on the stack. It is the address where we'll find the characters that we are actually pushing on the stack. And then the next one is str1, but we are pushing, but str1 is an array, so you cannot pass an array by value in C or C++. So the only way to pass it is to pass it by reference, which means we are actually passing the address of str1 and not the content of str1 on the stack. So we have this. Okay, we have this because str1 as a label is still an offset from the stack pointer, but that's it. No LD after that. Okay, we decrement the stda. That's how we push str1 on the stack. We are not pushing the content or the bytes of the array on the stack. We're pushing the address of the array on the stack, and that's why we do not have an LDAA in this case. Then we call the subroutine. Okay, so we call the subroutine text string and copy, which is decrement D and LDI a dot 5 plus. Okay, so this is one thing I noticed about the homework assignments is some people use dot 5 plus without the space between the dot and the 5 and the space between the 5 and the plus. The assembler won't even take it, okay, which means that program does not even assemble. And if the program doesn't assemble, I cannot imagine how people can debug it. So that's what I'm seeing in the submissions, which is kind of like, oh, come on. Do I have to put a JMPI after the bytes in the constant? The answer is no. You mean okay? You mean over here in on lines 147 and line 40, Martin? Yeah, we do not need to jump around that anymore because they're after the halt instruction and nothing will execute after the halt instruction. All right, so let's complete this. Okay, we push the return address on the stack. We got the return address in register A, so we do a stda. That pushes the return address, and now we can do a JMPI to the subroutine that's called text string and copy. When it comes back, we got three things sitting on the stack that are just the arguments, which we do not need right away. We don't need any more, I should say. So we have increment D, and increment D to get rid of the arguments. And the return value is still in register A. So this is where we call string length. Okay. So at this point, register A has the return value of text string and copy, but it's not on the stack. We have to push it on the stack first. So now we have a decrement D and an stda to push the return value of text string and copy on the stack. Then we call string length. Okay, so now we do the same thing, which is decrement D, because we just have to push the return address. The argument is already on the stack. So now we're just pushing the return address. So we have a decrement D LDIA dot 5 plus stda. So now we have pushed the return address on the stack. Then we JMPI to string length, which has not been implemented yet. We'll do it in just a moment. Okay. When that comes back, I have an increment D to deallocate the argument of string length. Okay. And the return value is now in register A, which we can then compare to 6. Now we want to see if register A is greater than 6, but greater than is not something that we can check easily. We can check less than really easily, but not greater than. So we still need to load B or C with a 6, and then we need a CMP. The CMP is going to be the other way around, which is CMP B, which has 6 in it, and A, which has the return value in it, because it's easy to check whether something is less than rather than greater than. Okay. So at this point, I need a conditional branch instruction, that can check whether something is less than or not. Okay. So depending on the return type of string length, I need to use the correct conditional branch instruction. And this is where things get a little bit weird. Okay. Because if you look up string length, okay, it will tell you that it returns a type. The return type is called size underscore t. I'm not sure whether it explains what size underscore t is, but it really is an integer. It is not unsigned. It is a signed integer, which is kind of odd. Okay, so let me look it up first, size underscore t, and make sure that that is actually signed. Okay, so we'll look it up. Size underscore t, is it signed or not? Okay, there we go. Oh, it is unsigned. Very good. Okay, that makes more sense to me. Okay, good, good, good. Because sometimes certain types do not make any sense. Size T is actually unsigned. So now that we know size T is unsigned, which JXI instruction should I use to perform the conditional branch? Not Z, because we are not looking for equality. We are trying to look for less than. Yep, Richard is right. Okay, we need a JCI because we are looking for less than. Yeah, that's okay. I think that's what you meant. C and Z, I mean, they're pretty close. Okay, so if it is less than, okay, if 6 is less than, yes, so if 6 is less than what the string has, then we go to the then branch. So I would call this main if one then branch, and then JMPI to the else branch. Now, how you want to structure your conditional statement is also entirely up to you. If you want to preserve the ordering of the then branch versus the else branch, this is how you do it. But you can always flip it so that you don't have to kind of perform the additional branches. Because doing it this way means I need to branch around the else branch. So I also need a continuation label, which I call end. So once again, I define all the labels. I come up with the structure of the conditional statement first, and then we fill in the content. So the then branch is corresponding to line 36. We just want to put a 2 into X. Okay, so that's LDI A with 2. That's my right hand side, and then the left hand side is just a little bit more complex, but not by much. So that's how we do the then branch. The else branch is pretty much the same thing. Okay, so we want to put a different constant into it. So we are looking at line 161 to line 164 and copy it to this point. And instead of a 2, we have a 16. And that's it. Okay, because after the conditional statement, there's nothing after that. So we are technically done. Okay, except we are not done because string length has not been implemented yet for this program. So we'll go ahead and I'm going a little bit over time, just so that we can finish the program. So now we have to implement string length. It is always good to implement something in C first and make sure that it works, right? So we want to look at string length, okay? And we basically, because we are trying to make this code to work in assembly, so we'll return an 8-bit signed integer, which makes this a very limited string length subroutine. Const char ptr, and this time I'm still thinking about whether to do it recursively or doing it non-recursively. Let's do it non-recursively, just so that it's easier to track. So tomorrow I can re-implement these two subroutines in a recursive way, but today I'll do it in a non-recursive way. So this one, we need a local variable, okay, to do the counting. So we have a counter here, which is initialized to 0. And as long as PTR is pointing to something that is not null, we need to do two things. Count needs to increment, and then PTR needs to increment as well. And when we get out of the loop, we just have to return count, and that's how we can implement string length. And in the C code, I will replace the system string length with my own. Okay, so ideally speaking, we should test this code in C first to make sure it works, and then we go back into assembly to implement it in assembly. But I'm going to skip that step and just implement it in assembly. Okay, so we have tags string length, and we'll define a few labels. We can count as my local variable, So we have TS string length, local var size to be count 1 plus, because we only got that one single local variable in this one. And then we only got one parameter too, which is just PTR. So PTR, now this is going to be an issue because we have PTR twice defined. One is in text string length and the other one is in the other subroutine. So it doesn't work well in assembly because every label in assembly is visible within the entire file. So I'm just going to abbreviate this one to P instead of PTR. If you want to use a prefix like text string length underscore PTR, that works too, but it does a lot of typing, so I'm not going to do that. So in this case, it's the string length local var size 1 plus. Okay, so now we have that done. And you can also just reuse the template that we already have. In fact, I can just kind of copy and paste a little bit of code here. In fact, we can copy and paste a lot of code here. So 6 lines, copy it over here. And this is going to be TSS length local var size. And the first one is using a subtraction so that we are allocating. The other one is for deallocating. That's why we are adding. And now we just have to initialize count to 0, LDIA with 0, LDIB with count, add BD, STBA, and then we have a loop. Okay, so whenever we have a loop, we have while one begin as the label of the beginning, while one end as the label to end the loop, to exit the loop, and then unconditionally we have a branch back to the beginning. There we go. So now we can go back in and fill in, how do we stay in the loop? So we need PTR to be pointing to something that is non-zero to stay in the loop. So we'll go ahead and compute PTR, the address of PTR first. So LDIA with PTR. Oh, it's just P, not PTR. I have to remember that. Add AD. That's the address of. I want to keep it around because later on I'll need it back. So we use LD to register B. So register B is the value of PTR, but we want to compare what it points to. So that means we have to do another one, LDC B. So C is whatever PTR is pointing to. That's what we are actually comparing. Then we have an AND CC to see whether register C is 0 or not. If it is, then it's time to get out of the loop. So we are going to branch to while one end corresponding to this function. So that's my condition. That implements the conditional part of the loop. So inside we have to increment count and also increment pointer. I'm gonna increment pointer first because I got everything I need to do that increment. So when you look at PTR, okay, we have to kind of track what each register has. Register A has the address of PTR, so we want to keep it around. Register B has the value of PTR, so it is B that we have to increment. And then we store it back to whatever A is pointing to, because register A still has the address of PTR at this point. Then we increment count. Okay, so we do pretty much the same thing. Count LDIA with count, add AD, and then we do a LD first. Okay, so that we know the current value of count. Increment that, and then store the incremented value, which is B, back to A, because A still has the address of count. That's about all we need to do to increment count. After we get out of the loop, we have to return the value of count, which is another LDIA count, add AD, and then we have a LDAA. And this time we use LDAA because we want the value of count to be stored in register A, because register A is what we use to return a value to the caller. So that should complete this program. And we go back to the C code first, okay? And the first thing we want to do, okay, since we are going to do this anyway, might as well do it the correct way. We want to compile first the C program, and it's okay, I forgot to do one change. Okay, so let's fix that. I thought we fixed that. So let's do it one more time. Okay, what is it complaining? Implicit. Oh, okay, I see. Oh, because I forgot to. I did not. No, I thought I did. Text string length is here. And then text. Oh, typo. It's text string length. Yep, there we go. Try that one more time. There we go. So this time it's only warning about a unused variable and a variable that is set but not used. So everything seems good. GDB strings. And I'm going to put a breakpoint on line 45. Run the code. Do a next instead of a step. Okay. And we get to the else branch, which is correct. But we still want to make sure that we did the string copy correctly. It definitely has that. And I think we can actually test string length here as well. So let me try that. String length and str1, and that should return a 3. Yep, it does return a 3. So we are good in the C code. The question now is, what about the assembly code? Now I have just written 200 lines of code, okay? A little more than 200 lines of code, but some are empty, some are comments, some are label definitions, without testing anything whatsoever. So do not do this, okay? Well, you don't have any programming, you don't have another programming assignment where you have to start from scratch, so it's a non-issue at this point. But regardless of the programming language, you probably don't want to write a whole lot of code without testing first, which I just did. So we'll see, how I'm going to pay for that, because I did not test, incrementally. So we'll check it out. So cat, what is the name? Strings, I think. Yep. Strings.ttp asm to x clip cell clip. Switch back to the assembler. There we go. And it looks like it assembled okay. And nope, there are errors. All right. So we're gonna have to fix those things first. There we go. We got a unresolved reference to str because that's before I changed the call to my own string length program. All right, so that's a pretty easy change. So we have to change this to refer to text string length. Okay. There we go. So switch back to the assembler. Paste the code. Go to RAM file. So looks like this time it's good because we can see version 2.0 raw, and we just need to download this the CSV file. Oops. Strings. There we go. And then switch back to, we'll pick this one. I have to make typos in the worst possible way. Alright, so this is the one that I want. Alright, well, at least it terminates, which is good. Then we go back to the trace analyzer. And by the way, all of these tools are available to you for the final. So, I definitely would consider using all of these tools, everything at my disposal, except for help from another person to get the to get the final done. Okay. So if you have been writing your own program and debugging your own program for a while, you probably have muscle and memory to do all of this stuff already. Alright, so we got this done, and we want to look for the halt location, because we want to locate the end of the trace right away. So let's see. Alright, so the halt instruction is at location BB. So this is one of the longer programs that we have written up to this point. So location BB in the trace is where we need to start going backwards to find out whether things happen correctly or not. So we look for BB in column A, like so. And there's the end. Alright. So we did store a 16 into location FA. So that looks good because we executed the else branch. So now the question is, did we actually copy the string correctly? So to understand that part, okay, I'm going to use a spreadsheet to look at how memory is used in this case. This is from yesterday. I'm going to make a new one for today. Alright, so we got location FF, FE, FD, FC. Let's see, what else do we need? We need FB, FA, F9, F8. Okay, so I'm just going to use these locations for now. We go back to the source code and also look at how memory is allocated first. So we look at the beginning of main. Okay, and then we look at main, and then we find out how we use memory in main. The last thing that we declared in main is str1. So str1 has the highest address, but str1 is an array of 4 characters in this case. So that means it's taking up 4 bytes from the top of the stack. It's using location FF all the way down to and including location FC. So all of these locations are really corresponding to str1 of main. The next one down is str2 of main. It's only using 1 byte because it is just a pointer. Now the pointer is later on initialized to actually point to the literal string, but as far as how much space it consumes in memory on the stack, it's only using 1 single byte. And X is the last one, so X has an address of location FA, and we did see in the trace that X has it got a value of 10, which is 16. So now we want to look at locations FC to location FF, because if the string end copy happened correctly, it should have copied HI exclamation point and a null terminator to exactly these 4 locations. So we want to look at the updates of location FC, FD, FE, and also FF in the trace. So now we go back to the trace analyzer, and this time we focus on column B because we want to look at what kind of values are written in those particular cells or memory locations. So this is on the side. We want to look at location FC first. So Control H, we want to find location FC. There we go. Now this is just pushing FC, on the stack as a parameter. So it's not really updating location FC. It's updating location F5 as an argument to string and copy. So this is not what we're looking for. We can actually look a little bit more specifically, looking for star FC equals to. Okay, so that will make it super specific, and that's where we get the 2-1 in hexadecimal. If you look up a ASCII table in 2-1 in hexadecimal is not what we want actually. Let me see what it is. So 2-1 in hexadecimal is the exclamation point. So it did not copy correctly. So let's look at FD. FD got a null character. So the HI is somewhere else. So let's see how FB is used. FB is getting BC, which looks like a return address. So it did not copy HI exclamation point and the space. It only copied the exclamation point and the null character into it. So the program did not do what it is supposed to. And let me look up HI in this case. H is 68 in hexadecimal. So let's see if it's even mentioned anywhere within this column. And it is not. Okay, let me try that one more time. I think I typed something incorrectly. Okay, H is 68, and we want to find it. Nope, 68 is copied to location FA. Or did I just have a brain fart? Nope, I did not have a brain fart. FA is the wrong location to put that. So it's using the wrong location. The string is starting at this location and it's moving its way up like this. Okay, well, that's fine. We want to find out why it's doing it like this. So this part is debugging, which is also something that you can do on Thursday, is to utilize the trace analyzer to help you debug. So now that we know the program is not behaving correctly, we want to find out why it is overwriting location FA with 68 instead of using location FC for that purpose. My first suspicion is okay, so the first question is, where is this happening? It's happening at location 24. We go back to the Assemble tab, look up location 24 to figure out where in the assembly code is doing this. So this is location 24, corresponding to the store instruction. And it is in the first loop. Okay, so it's still in the first loop. And the register C has location FA. And we did use the pointer. So now the question is, are we using the correct offset for pointer? So for that, we need to go back to the trace analyzer, and that is corresponding to location 20 in the trace. So we go all the way back to location 20. So this is PTR, the offset of PTR from the beginning, from the stack pointer, and this is where it is supposed to be at in on the frame. F5 is the beginning of the frame of string and copy, and C has FA in it. So that means the initialization of PTR may be incorrect. So location F5 should be initialized at some point. Yep. So location F5 is initialized to FA at location 0F. So now we track down location 0F, which is here, and we want to see whether this is correct or not. So we copy the destination to register A, and then we copy the destination to the PTR, so that seems correct too. Okay, so that looks good. So now the question is FA the correct thing that we find on the stack? All right, so going back to here. All right, so we need to look at the call of the subroutine at this point. So FA is all right, so when we call the subroutine string and copy, we have to pass the parameters. F9 is supposed to be the count, and that is the 4. And then location F8 is the second parameter, which is the source. And then location F7 is the destination. So that is already off from what I'm expecting. So location F6 is the return address to main. Location F5 is the local variable PTR. So the local variable PTR is at the right place, but it's not getting the destination. The destination is supposed to be location FC, unless I calculate that one incorrectly. So now I need to look at how things are pushed on the stack to see whether the destination is pushed correctly to location F7. So location F7 is FA, so I'm already using the wrong location to push as the destination. So now we look at location 90 and find out why that is incorrect. So we look at location 90 in the assembler, which is this one here. And the way we calculated that is str1, the offset added to the stack pointer. Okay, I know why. Okay, this is something that we talked about just yesterday. Let me see whether people are still with me or not. We still got a whole bunch of people. Okay, so one thing that we learned from yesterday's lecture is what? We got what did we learn about the calculation of the parameter for the second call of Fibonacci, the second recursive call of Fibonacci, when we need to find out where local not variable, but where parameter n is located on the stack? I think Richard knows exactly what I'm talking about. Offset by 1, exactly. And I forgot about that today. So I pushed the number of bytes for string and copy. I pushed the literal string, which is my source, and then I'm supposed to push the address of str1, but at this time, how many more things are on the stack compared to on line 157, right after I did all the allocations for the local variables? So on line 170, I have how many more bytes on the stack? In other words, the stack pointer is now adjusted down by how much? Not 4, it's 2. It's 2 because we got the third and second argument on stack already at this point. So only 2 bytes in addition to, there are only 2 extra bytes used on the stack at this point, and that's why I have to compensate for that using the 2 plus. Is that okay, Richard? Because you wrote down 4 more. I just want to make sure that we understand why it is just 2 more instead of 4 more. Okay, all right, excellent. All right, so, but the most important point is not that Tech made a mistake in his program. The most important point is how I found that mistake using the trace analyzer. Is that process okay? I mean, because if that is much more important than some of the other stuff that we talked about today, is actually the logic of how I found the bug. How I use the trace to kind of go backwards and go like, this doesn't look good. It's not. This is not where it's supposed to be. Which everything started with this picture. So are there any questions about this picture first? Okay, how the stack is supposed to be used? Because if this table, if this picture, how the stack is supposed to be used, if this diagram is not right, then I wouldn't have the information that I needed in order to go like, hey, I'm putting the bytes at the wrong location on the stack. Are we good so far with that? Okay, Sakil said it's okay. All right, so now that I have quote unquote fixed the program, we'll do it one more time. Okay, we want to double check and make sure that this one works, because I want to give you this code so that you can do the same thing that I recommended you to do yesterday, which is going through every single line and understand why it is there. Okay. All right, so we'll go ahead and do the same thing. And paste the program into the assembler. Okay. All right, and then download it as the CSV. And then rerun the program, collecting the trace. And then go back to the trace analyzer. So this is a pretty typical workflow, when I write programs in assembly, in this particular environment. Strings.tsv, it's already selected. Okay. And we're going to do the same thing. We'll locate the halt instruction, which should not have changed. I think it's location BB, but we'll double check just to be sure. Yep, so it is still at location BB. So in the trace analyzer, we go to the analysis tab and find the end first, and then we go back to confirm everything else. So Control H, look for BB, and that would be the end of the trace. And now we go back. So location FA getting 10 is correct because we went through the else branch. So now we want to look at the bytes at location FC to location FF. So we highlight column D, and then we look at the update of FC first. So FC should be getting the ASCII code of lowercase h. And there's no entry. Oh, I'm looking at the wrong column. Okay, done. Should be looking at column C, not column D, because column D has to do with register change. So that's my bad. So FC equals 2. 68 is correct, okay, because 68 in hexadecimal is the ASCII code of lowercase h. But it doesn't hurt to confirm all of the other ones. FD should be high, HI, so that's 69 is correct. And then 6 FE, I mean FE, excuse me, FE is the exclamation point, which is 21 in hexadecimal. Yep, okay, so we got that. And location FF should get 00, but it may not show up at all because it's already 0 to begin with. So it would probably not have, oh, it does have 00 here, but I'm not sure whether it's done by the correct place. Let's see, location 41 in the assembler. Yep, well, it does work. It's the second loop of the string end copy subroutine. So it did copy a 0 into that location. Okay, cool. All right, so that's the verification of this program actually working, is to look at those byte locations. But the most important part, okay, I cannot start debugging the program unless I have this available to me. Unless I understand how the locations on the stack are being used, I cannot go into the trace analyzer and check, okay, did I put something like this over here? And did I put something like this over here? So I need to mentally have a picture of all of this stuff already in order to debug the program. All right, so it's a little bit long today. Okay, it's about 2 hours. But do we have any questions before I get off of live stream? You can consider this, as another prep for the final. Because if I give you faulty code to implement a particular C code, the C code is working. Okay, so that means you can use a C compiler to see how the C code works. But the assembly implementation is incorrect. That means, first of all, you can run it through the assembler first. Okay, the assembler will catch anything that is a syntactical mistake. But then when you run it through the trace analyzer, that will basically leave behind a trace. But in order to interpret the result of the trace analyzer, you kind of need to know how the frames are set up, how function calls are supposed to happen and how functions are supposed to return. So that way you can anticipate what locations should have what in the program. And it also would not hurt to start commenting the program so that you can identify which part of the code is the allocation of local variables, which part is actually calling, which part is pushing the arguments, which part is freeing or deallocating the arguments, which part is returning back to the caller. So identify all those big chunks first would always help in terms of matching the assembly code to the C code first, and then you can look for discrepancy between the two. All right, so I'm not seeing any questions. So what I'll do is I am going to get off of live stream, and then I'll stay online to see if people have any questions. So once again, there are no more homework assignments. I don't think I'll give you any assignments today nor tomorrow. We'll just have the final on Thursday, and it's going to be a midnight to midnight kind of deal where the exam opens at exactly midnight of Thursday, and then you have close to 24 hours to submit your answer. But I'll give you more details of the format of the final tomorrow once I kind of put some thoughts into it so that I can kind of help to restrict what type of exam is going to be. Exam 2 is still being graded, so it's not there yet. But you guys can all look at your exam, okay, what you turn in, and look at the key that I have provided. If you have most of the key concepts, or the key steps, included in yours, you're gonna probably do, you should be doing okay. And June is typing, so I'm gonna wait until I can answer June's question before I stop live stream. I will do the best that I can do. Certainly I can put in exam 1 into Canvas. I was about to say Discord, but I'll put it into Canvas. But exam 2, I'm still in the process of doing it. but I should be able to get it done before the final. So between tomorrow and tomorrow, I should be able to get exam 1 and exam 2 into Canvas. But some of the homework, some of the labs do also need grading, but they don't count for a lot of points. The exams are the ones that got a lot of points. All right, so there's that. So I got some grading to do today and some grading to do tomorrow, and also to come up with the questions for Thursday. So there won't be any scheduling on Thursday because I'm just gonna make it available for 24 hours, and people can allocate their time any way they want within the 24 hours. But the downside is I won't be on Discord for the entire 24-hour period. So that means I will get to Discord when I wake up, and I may or may not be able to stay until midnight at the end of the day. So that's kind of the downside of not having a scheduled time slot, is I may not be on Discord all the time. Okay, all right. So if there are no further questions, I'm going to stop the live stream and be back in 10 minutes.